Hi everybody, I'm Haaren. I'm a network software engineer at Intel. I work on optimizing software data planes, so particularly OVS has been a recent focus of mine. Part of the tasks that we have is to try and make the DPDK based or Userspace data path go a lot faster. We've been on this for a while, so you may have seen presentations from us and the team in Intel here doing various optimizations to previously DPCLS and refactoring things there and cleaning up some of the code to make it go faster. This talk is the continuation of last year's and the year before, really. So what we'll be talking about is trying to reshape parts of the data path to make it more dynamic, more flexible, and generally just more performant. That's really the goal. The way we're going to approach the talk today is I'll have a few slides. We'll talk about the current state of the software data path, particularly in the 2.14 release, what we have, what that looks like. So I'll graphically represent the design or the architecture of the data plane. And then for the 2.15 release, we're working on some patches to improve the DPIF component or the data plane interface, which is kind of the glue code that puts together receiving packets from a DPDK device, Miniflow Extract, EMC, SMC, partial hardware offload if that's enabled, and DPCLS or the wildcard lookup of the packets, all the way through to executing the actions on a batch. So the part there that we'll be optimizing is this DPIF, which is kind of the glue code, as well as the Miniflow Extract implementation itself, and I'll talk about some optimizations we can apply there. So let's dive into the current state of the software data path, and then we'll look at more detail as we go along. So as we can see here, the OVS 2.14 data path has a certain kind of layout, a representation, as you can see here. Particularly if we look from the bottom left, we'll see a network card. DPDK RX moves into the scalar DPIF, the horizontal gray box. As a start of the DPIF, we'll call Miniflow Extract, so MFEX for short. Then EMC and SMC logically are in that stage in the DPIF box. I haven't represented them here, but logically they would be there. And then the DPCLS component would be called. You can notice the DPCLS here has a different color scheme, so the DPCLS selection or SEL box. We have two implementations of the DPCLS today based on the CPU ISA, so if your CPU supports AVX512, we can run a different version of that DPCLS code, which happens to be more performant in many cases. And what that allows us to do is to basically, at the DPIF level, call into this DPCLS selector, so it uses a function pointer to select the best available ISA to run that workload. It's a very good design pattern. It allows optimizations, but also abstraction. So it allows a fallback version in the code that will always run on every CPU, and it allows us to optimize to utilize the CPU's full potential using this function pointer. So that's a pattern that we're continuing to deploy in the future of OVS's data path, particularly in 2.15. We hope to introduce another function pointer at the DPIF level. If we move to the DPIF level function selector, what we can see is the diagram now is updated. It is also got a DPIF selection at the start of the RX path. So once we receive a burst of packets from the DPDK or from the NetDev, it allows us to choose two DPIF paths. And again, one of those is now accelerated using SIMD ISA, in this case AVX512. That affords the CPU or the code some flexibility in how it does packet batching in particular. And there's some optimizations around how we lay out data structures and how we can use these CPU instructions to effectively and more efficiently batch packets. So that's the reason that this DPIF component will actually benefit from using AVX512 or from these optimizations. Again, this function pointer is just a selector. It enables us to switch between those two implementations, and both can be active at the same time in theory as well. Let's continue and have a look at the Miniflow Extract implementation as well. Previously we saw this gray box in the middle, the Miniflow Extract implementation. Now we see it's also become a function pointer and is now a runtime selectable component. In this case, we add another implementation using SIMD ISA, AVX512 in this instance, to accelerate packet matching in particular. And we can get some more optimized versions of this Miniflow creation based on the input packet by using a different approach to the problem. And I'll talk about some more detail in the next slides. For now, understand that the data path of OVS in 2.14 was a little flexible in DPCLS, but quite stiff and rigid in what parts of the code implemented what functionality. But with our 2.15 implementation changes, or proposed changes at least, we are hoping to make that a lot more dynamic, to be able to add the CPU's value and SIMD ISAT to all elements of the data path. So right from the DPIF, where we receive packets, through to the batching, to how Miniflows get extracted, to doing the DPCLS wildcarded lookups, and then providing those actions to be processed at the end. So having introduced these concepts like the DPIF function pointer and the Miniflow extract, what does this actually look like for the user to use, to consume? For the case of the DPIF, let's look at that first. And it's just a single command to run. It'll be added to the OVS app-kettle command. So as part of that, the DPIF-netdev/DPIF set command will allow the user to change the DPIF implementation. So as we can see, we have two implementations, and by giving those implementations a name, it's relatively trivial for the user to switch that implementation on the fly. The user can specify which of the implementations they would like to run, meaning that they can run, for example, DPIF_AVX512 to enable that implementation. They can also revert back to the scalar implementation by running the same command, but now with DPIF_scalar. So let's have a look at how DPIF will actually work in terms of batching packets using AVX512. Here on the top right, you can see that we have one packet batch, so it represents a burst of, let's say, 8 packets or 9 packets. As processing happens, DPCLS will create sub-bursts, if you like, that each sub-burst needs a different rule applied. So in this example, we can see that packets 1, 2, 4, 7, and 8 or so have matched on the first rule, and that the other packets have classified against 2 other rules. So you can kind of see we have 3 logical sub-batches that we want to now execute. It's a sparse representation of the burst. So the burst is now being kind of partitioned into 3 segments. And those 3 segments will each need a different action applied. That's how fundamentally OVS's actions get executed at the packet batching level. And there's an AVX512 compress instruction that handles exactly this case. It takes a bit mask and it takes a lot of input data, and then it creates submasks or subbursts using that information. So that's what we can do, and that's the reason for enabling this DPIF AVX512 implementation, is that the batching of packets can use this AVX512 ISA, so these instructions specifically for compressing data horizontally inside registers. And that's exactly the type of workload that OVS has in the DPIF, to take larger bursts of packets and to compress them to smaller ones. When I mentioned in the cover letter of the patch set that we convert a memory-bound problem into a compute problem, this is the fundamental tactic used behind that. So in the scalar DPIF, memory is used to store these batches and to build up these batches in memory. And that's basically by using pointers to dereference and to change where stores of packet data are going. In this AVX512 implementation, that gets turned into fundamentally a compute problem, where this compute instruction, or AVX512 compress instruction, is used to achieve that compute. And that fundamentally makes the CPU more capable and more performant in performing this particular task. Next, let's look at Miniflow Extract and understand more about what that can give us as a performance benefit when we use AVX512 and specialize this Miniflow Extract behavior into optimized code. Initially, we have our scalar Miniflow Extract. The way that works is it takes a very scalar approach and protocol by protocol approach to parsing a packet. This is very flexible, and in scalar code is quite performant. However, in AVX512 code, we can approach the problem differently to give us a much higher performance. To enable this AVX512 Miniflow Extract implementation, we have an optimized version that we can set a function pointer, just like DPCLS and DPIF, as discussed previously. And the command to do that is, again, using OF app-kettle. In this case, it's a DPIF netdev miniflow optimize. And after that optimize, we can pass the name of the implementation that we would like to use. In this case, we could use something like AVX512. And that will go and basically change the function pointer, or start the procedure of changing this Miniflow Extract implementation. Before we get more into the command details, let's have a look fundamentally at how AVX512 implements Miniflow Extract and what that looks like. I'll use some graphics here to try and showcase really what's going on from the CPU's point of view. This is a graphical representation of what Miniflow Extract would look like with AVX 512. On the very top, we can see a packet. That's the linear data inside a packet header, so it starts with an Ethernet header perhaps, and then with some IP or some UDP inner packets. This is ultimately the traffic profile that the user would like to have parsed as performantly as possible. Underneath that, we see two other elements of data. There's a pattern, which is consisting of a mask and some values. And fundamentally, the way we're going to approach masking the packet and matching values to it is a very SIMD approach. Every byte in the packet will have a mask and a value to compare to. And this allows us to probe simultaneously for an Ethernet type of perhaps OX800, which would be the IPv4 standard Ether type, and then perhaps a UDP next proto at the IPv4 layer of OX11 or 17 in decimal for the UDP inner. And because this is all done in SIMD, single instruction, multiple data, all these checks and all these comparisons can be done at once. I've updated the diagram here. Now you can see the AND, so a bitwise AND operation occurring across all the data in parallel, and it's being compared equal, so compare equal or equals equals in scalar C code, to a particular value in that pattern. So by providing these mask and pattern values, we can detect any type of traffic pattern layout. It's really the layout of the packet data that's interesting here, not necessarily the contents of what MAC address is it or what particular IPv4 things are set. It's the layout, the data shape in a way that is the interesting thing that we really need to understand here. So by masking and comparing to a known value, we can exactly know what that layout of that packet is. In the next diagram, we can see that by knowing the data layout in the first place, as the previous mask and value compare has given us, we can reshape or we can shuffle, being the instruction used on x86, 64 platforms, where we shuffle the data around, and that basically means reorganizing or reshaping the layout of that data. And by providing the right input to that shuffle instruction, we can build a Miniflow data structure. So the Miniflow is a known data structure for any traffic type. And because we've previously compared a very specific traffic type, so for example, Ethernet, IP, UDP, we can now build that Miniflow out of a single or a few shuffle instructions because we knew exactly what the data input layout was and we know exactly what the Miniflow output layout should be. So the power here of parsing is not by going protocol by protocol by protocol like Miniflow Extract in the scalar sense, but it's actually by understanding one packet across multiple protocols and probing them all in parallel using these very powerful SIMD instructions. That's the fundamental reason for using this type of Miniflow Extract. As you can imagine, there are a lot of traffic patterns. This can cause some complex kind of enabling because each traffic pattern, based on the data layout, will require a different shuffle or a different way to build up that Miniflow. So there's been a lot of effort in developing and enabling this work to allow users to set their own traffic profiles at runtime. As you can imagine, if we had to do this at compile time, the development workflow of a programmer to write this code to then go upstream to OVS and then to later actually be deployed would be very, very long. By making it runtime, we allow users to essentially inject their preferred traffic type or their pattern into OVS while it's running. We compare the Miniflow that gets built based on their input data with the official scalar version of OVS's Miniflow Extract. And by comparing those two, we can understand if the correct Miniflow is being built or not. So this allows a huge amount of flexibility to the user that they can specify what traffic patterns they want at runtime. And fundamentally, that is key to enabling this. There is no reasonable way to guess what traffic patterns users are running, to try and upstream those into OVS and then to later have customers use them. That's not something that's possible. Instead, what we need to focus on is a way that we can enable this at runtime, and that's what we've enabled in this particular patch set. So there is some complex angles of this. From a usability performance kind of trade-off point of view, this command focuses on performance. It does make it a power user feature. It does mean that it's a little harder, particularly when starting out maybe, to understand why we need all this data in this command. The way that we hope to help people to understand these things is by providing documentation, providing examples for common traffic patterns, and being a point of contact that if someone does have a question for a specific traffic pattern, that we can help to build that particular input command for the community. Having reviewed how Miniflow Extract with AVX512 actually works, and having understood what these masks, like the value mask and the shuffle mask and things, actually are used for, let's have a look at what that command looks like to enable such a feature in OVS. Initially, we talked about the command itself, which will be Miniflow optimize, then the name of the implementation, for example, AVX512. After that, there will be a longer string which contains these various masks and data values that are required for this operation in SIMD to occur. First of all, we have the actual match mask and match values. Those are used to filter the packet type to understand which parts of the packet the packet layout, the packet data imply the packet layout, and what values we expect there. Those are used to determine the packet layout and to probe if we've matched that packet layout, yes or no. The next, we have the shuffle index. That's essentially the byte movement from the packet to the Miniflow. The user specifies this as it maps the specific traffic pattern to the Miniflow that wants to be built. There are also some other fields, like a mask in the shuffle, to zero out parts of the field, as the Miniflow sometimes contains null or padding where the packet does actually contain data. So the packet can be seen as a compressed form, and the Miniflow actually is slightly larger, but puts things in a very regular and generic pattern, which makes OVS or the DPCLS and the processing later in OVS much more performant because the data is laid out in such a generic way. Those familiar with OVS will be familiar with the Miniflow data structure and why it is so useful. Next, there are a number of other parameters that we can pass to this particular command to make it more usable and easier to validate. Particularly, there is a test packet which allows the user to pass in an arbitrary packet. We allocate one DP packet while this Miniflow extract is running. We try and do the Miniflow extract of the packet using the scalar implementation as well as this Miniflow optimized version. So we'll have the scalar version classify the test packet, and we'll have the AVX512 pattern based on the user's input also classify this same packet. And then we can check the Miniflows to make sure that the Miniflow is identical. If the Miniflow is identical, it means that that packet was parsed perfectly and that there's no errors in the shuffle masks in this case. In order to make that as easy to do as possible to generate this test packet, we're looking to use Scapy, a very well-known networking tool, to actually output, or firstly to craft the packet, and then to output the hex values that we will later input to the command to actually have AVX512 enabled Miniflow extract in OVS. For more details on how exactly the command works and for examples, please investigate the latest patch set version. At the moment, we're working on a V5. There will be future revisions where we're progressing on almost a weekly cadence at the moment for large improvements and changes to how usable this is, how well documented it is. Proof of concept is actually running. It has been for quite a while with the DPIF and the AVX512 Miniflow extract optimizations. We're seeing significant performance improvements. We hope to publish some of the numbers and the results thereof soon too. So there's a lot of ongoing work in this area. I hope that it's of interest to investigate, and please do provide any feedback and review these patches on the mailing list if you have an interest in performance of the OVS software data plane. Thank you for listening, and I hope this talk has been informative for you. I'll welcome any questions both to my email, harry.van.haaren@intel.com, or by contacting me via the mailing list or any other means is fine. Thank you, and have a good day.